and welcome to my Lab 4 report. The purpose of this lab is to collect observational data of a magnet falling through a conductive copper tube, to model the magnet and tube interaction computationally, and to compare the computational predictions with the observed data. The models used were the actual experiment and a glow script simulation. A preview of my results is that the time to fall in the experiment was 2.954 seconds, and the computational time to fall was 15.391 seconds. The system is a falling magnet, which had mass 24.3 grams. The surroundings were the copper tube and everything else. The copper tube was 0.918 meters long, had an outer radius of 0.15 meters, and a thickness of 1 millimeter. Initial conditions were that the magnet was at the top of the copper tube and it was not moving. Fundamental physics principles include the magnetic field, flux, electromotive force, and current. Flux is the integral of the magnetic field dot the area. Electromotive force is the derivative of flux, and then current is the electromotive force over R. Magnetic force is I delta L cross B, and gravitational force is negative mg. For the experiment, we dropped a bar magnet down a copper tube and videoed it. We recorded the time the magnet entered the tube and the time it exits the tube to find the difference. We repeated this 5 times and found the average time to fall. These are our results from each trial, and the average time to fall was 2.954 seconds. For the coding part, these are the constants, which have the tube stats and the magnet stats, and mu mag equals 6.655, which I found in previous lab. To code the magnetic field, which I also did in the previous lab, we translate the formula into Python. Code the flux, we translate the formula into Python again, and then the current is the derivative over the resistance. Net force and movement, we found the magnetic force and the gravitational force and combined them, and then we also updated the bar velocity and position. With mu equals 6.655, it took 15.391 seconds for the magnet to fall through the tube, which is unrealistic. But if we switch mu to 3, then the time in the tube is only 3.145 seconds, which is much closer to the actual value. We dropped the magnet north side up so the magnetic dipole moment points down. As the magnet drops, its flux increases in the downwards direction, so the induced current must create a magnetic field that increases in the upwards direction, so the induced current has to be clockwise. This means that the red is clockwise and the blue is counterclockwise. If we switch them so that red is counterclockwise and blue is clockwise, the magnitudes of each stay the same, so the time to fall remains similar to before. There is a difference of 12.437 seconds in the experimental versus computational model, which is quite a big difference. As I said before, to make the computational system more accurate, we should use a more realistic value for mu, such as 3. The graph has the velocity starting at 0, then increasing quickly to its maximum, before slowing down to a constant plateau for most of the time, then quickly increasing at the very end. This shows that the magnetic braking force mostly stays the same until gravity overpowers it, and the tube is over. Assumptions made were that there's no air resistance impeding the magnet's fall, and that the mu from Lab 3 is valid. As I said before, there was a 12-point-something difference in the experimented versus simulated time to fall, but only about a 0.1 difference if we used mu equals 3. Possible sources of error, as I have said multiple times, is that mu is unrealistically large, but also that the recorded video timestamps are not exact. As R approaches 0, I approaches infinity. Higher current means higher magnetic braking force, meaning the magnet will fall slower. Holes or slots in the tube would intermittently interrupt the loop of current at any particular point. Less current means less magnetic braking force, meaning the magnet would fall faster. Thank you.